All right, this is section 1.5 on infinite limits. So our definition of infinite limits, remember this is the technical math definition. Let f be a function that is defined at every real number in some open interval containing c, except possibly at c itself. The statement, the limit as x approaches c of f of x equals infinity, means that for each m greater than 0, there exists a delta greater than 0, such that f of x is greater than m whenever x minus c is in between 0 and delta. So basically that means the limit as x approaches c of f of x equals infinity if there's always a bigger value as I get closer to the c value. Similarly, the statement, the limit as x approaches c of f of x equals negative infinity means that for each n less than 0, there exists a delta greater than 0 such that f of x is less than n whenever x minus c is between 0 and delta. So the limit as x approaches c of f of x equals negative infinity if as I get closer and closer to c, there's always a smaller and smaller y value. To define the infinite limit from the left, replace 0 is less than x minus c is less than delta with c minus delta is less than x is less than c. To define the infinite limit from the right, replace it with c is less than x is less than c plus delta. We'll get into those a little bit. But these limits fail to exist due to the unbounded behavior of f of x. Our function goes way up to infinity or way down to negative infinity. So those limits do not exist. So let's determine the limit of each graph as x approaches 1 from the left and from the right. Each graph has a vertical asymptote at x equals 1. So for this first one, the limit as x approaches 1 from the left of f of x. Well, as I approach from the left, I'm going up without bound, so that's infinity. And the limit as x approaches 1 from the right of f of x. As I come in from the right, I'm going up without bound to infinity also. For the second one, the limit as x approaches 1 from the left. Well, as I come in from the left, I'm going up forever to infinity. And the limit as x approaches 1 from the right. Well, as I come in from the right, I'm going down forever, so that's negative infinity. Vertical asymptotes are next. If f of x approaches infinity or negative infinity as x approaches c from the right or the left, then the line x equals c is a vertical asymptote of the graph of f. So you've got a couple pictures here. This first picture A has a vertical asymptote at x equals negative 1. Because that would make the denominator 0, it's our vertical asymptote. In the second one, we have two vertical asymptotes at x equals negative 1 and at x equals positive 1. You can have as many vertical asymptotes as your heart desires. So our theorem 1.14, vertical asymptotes. Let f and g be continuous on an open interval containing c. If f of c is not equal to 0, g of c equals 0, and there exists an open interval containing c such that g of x is not 0 for all x not equal to c in the interval, then the graph has a vertical asymptote at x equals c. So what this means is that the numerator does not equal 0, and the denominator does equal 0. That's how you get a vertical asymptote. So let's find all the vertical asymptotes of each function. This first one, pretty straightforward. We just set the denominator equal to 0. So either 2 equals 0 or x plus 1 equals 0. So our asymptote is that x equals negative 1. For the second one, we need to factor. So the numerator does not factor, but the denominator becomes x plus 1 times x minus 1. Set each of those factors in the denominator equal to 0. We get x equals negative 1 and x equals positive 1 as our asymptotes. And for letter C here, cotangent of x. Remember that cotangent is cosine over sine. So we'll have asymptotes anytime the sine of x is equal to 0. Well, sine of x equals 0 at 0 and pi, 2 pi, 3 pi, 4 pi, 5 pi, all the whole values of pi. So we'll just say x equals n pi are my asymptotes. let's find the vertical asymptotes of this one. Well, we start off by factoring, but we want to factor the numerator and the denominator. So I factor the numerator into x plus 4 times x minus 2. And my denominator is x plus 2 times x minus 2. Now is where you have to be careful. Because you have a factor of x minus 2 in the numerator and denominator, that's actually a hole in the graph, not an asymptote. Our only asymptote is the one that doesn't cancel, x equals -2 when we solve it. So be careful of those holes, they are not actually asymptotes. So now let's find each limit. The limit as x approaches 1 from the left of x squared minus 3x over x minus 1. If I look at this, I can't factor anything. I could create a table of values, say x and y. I want to approach 1 from the left, so I'd say 0.9, 0.99, 0.999. I would grab my calculator, enter that as y equals, and then y1 of 0.9 is 18.9. Plug in 0.99, I get 198.99. Plug in 0.999, 1,998.999. I see that it's getting very, very large. The other way to go about this is to look at our graph. So I've already typed the function in for y equals. If I graph it, approaching 1 from the left. So I'm coming in from the left. Notice my graph goes way, 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 way up. We assume that limit is going up to infinity. Now I do from the right. Same function. I could choose values to plug into a table. I could do 1.001, 1.01, 1.1, and do the same thing. 1.001 gives me -2,000.999. If I plug in 1.01, I get -200.99. And if I plug in 1.1, I get -20.9. As we're going this way towards 1, they're getting very, very large and very, very negative, so it equals -infinity. That is supported by my graph also. Coming in from the right, it is going down, down, down. Couple properties of infinite limits. C and L are going to be real numbers here, and F and G are functions, so the limit as x approaches C of f of x is infinity, and the limit as x approaches C of g of x is L. So sum or difference. The limit as x approaches C of two functions added together. Remember, we could separate that. The limit as x approaches C of f of x is infinity, plus or minus g of x was L. This basically says infinity plus or minus L is infinity. For the product, you multiply them together. This is saying infinity times L is either infinity or negative infinity, depending if L is positive or negative. So infinity times a positive number is infinity. Infinity times a negative number is negative infinity. And the quotient, the limit as x approaches C of g of x over f of x. That means L over infinity. Essentially, dividing by infinity gives you 0, is the idea of it. Similar properties hold true for one-sided limits and for functions whose limit as x approaches C is negative infinity. So let's try these. The limit as x approaches 0 of 1 plus 1 over x squared. Well, we start out by breaking it apart. The limit as x approaches 0 of 1 plus the limit as x approaches 0 of 1 over x squared. The limit as x approaches 0 of 1 is 1. The limit as x approaches 0 of 1 over x squared. Well, I could try values from either side, or I could take a look at the graph to see that it approaches infinity. And 1 plus infinity means my entire limit approaches infinity. The limit as x approaches 1 from the left of x squared plus 1 over cotangent of pi x. Well, the limit of my numerator, x squared plus 1, I can just use direct substitution. I get 1 squared plus 1, which is 2. My denominator, the limit as x approaches 1 from the left of the cotangent of pi x, well, the cotangent of x is actually not something I can use direct substitution for. So I could take out my handy dandy graph. To graph cotangent of x, I do 1 over tangent, and I want pi x. Graph it as I approach 1 from the left. All right, to take a look at this, we may want to use the trace feature of our calculator. Get on the, oh, I'm approaching 1. What am I doing here? All right, as I approach 1 from the left. Yeah, way too far. Here we go. X is close to 1, y is negative, and getting more negative before it jumps up. So that is negative infinity. So 2 divided by negative infinity, any number divided by infinity is always 0. The limit as x approaches 0 from the right of 3 times the cotangent of x. Well, we could look at this. Oops. Y equals the 3 times the cotangent is 3 over tangent. And I graph it. As I approach 0 from the right, notice my graph is going up, up, up forever. So that is infinity. And the last one here, the limit as x approaches 0 from the left. Well, we break that apart. The limit as x approaches 0 from the left of x squared plus the limit as x approaches 0 from the left of 1 over x. The limit as x approaches 0 from either side of x squared is just 0. The limit as x approaches 0 from the left of 1 over x, remember that graph looks something like this. So as I come in from the left, I'm going down to negative infinity. And 0 plus negative infinity is negative infinity. All right, that's the end of those examples. You're going to have some practice.